part-time. Okay, so welcome everyone to the first part of this book. So what are we going to do in this chapter? The authors tell us in chapter 1 we will make our first contact with Pytorch, understand what it is and what problems it solves and how it relates to other deep learning frameworks. Then in chapter 2 we will take a tour giving us a chance to play with models. Honestly, chapter 2 is super cool, and which have been pre-trained on Fantask. And then chapter 3 gets a bit more serious and teaches us basic data structured using Pytorch programs like the tensor. And then chapter 4 takes us in another tour, this time across ways to represent data from different domains as Pytorch tensors. Then we have chapter 5, which unveils how program can learn by looking at examples, right? So the whole concept of machine learning. And then chapter 6 supports like the fundamentals of, neural networks and how to build a neural networks with Pytorch. Then chapter 7 tackles a simple image classification problem, and chapter 8 shows the same problem how can be cracked in a much smarter way if instead of using like a neural network you use a convolutional neural network, which is another type of model architecture. So by the end of part 1 we will have what it takes to tackle a real problem. We, we will have what it takes to tackle a real world problem with Pytorch in part 2. Okay, so let's jump straight to it and see what this first chapter will cover. So it covers how deep learning changes our approach to machine learning, understanding why PyTorch is a good fit for deep learning, examining a typical deep learning problem, and the hardware that you will need to follow along with the examples. So important. I'm not gonna be covering this last point, basically because we have already talked about that, right? So I want to leave that aside, and if you want to work that, just like watch video number 2. So it starts by defining artificial intelligence, and it says, and what I really like is it would be it would be disingenuous to assert that today's machines are learning to think in any human sense. So it's a reflection of what it really means to think and what it really means intelligence. And it says that's an area with a lot of hype, but what we have truly discovered is a general class of algorithms that are able to approximate complicated nonlinear processes very effectively, which we can use to automate tasks that were previously limited to humans. And that's kind of why we get this fake impression of intelligence appearing. But I think that the authors are being it's a fantastic definition. So what I'm going to skip now to another paragraph, I think it's very nice, which is what they call the deep learning revolution. And what they explain here is the difference between machine learning is this whole idea of instead of hard coding each step of the task, you learn to do by examples, right? So think about it in the following way. In previous times, you would give, a program the code, and then that would process data. And now it's the data itself that writes the code. That's a very powerful paradigm shift. And that's what they refer in here, right? And that would be machine learning. Then what's the machine learning difference with deep learning? And they say deep learning is a subset of machine learning, right? And the key difference is um, feature engineering. And I think there is a very nice picture here that shows that. And they say, before this paradigm shift in machine learning, that's the way we used to do it. We had data, and then you, as a data science, would handily craft features, and then you will have the machine learning algorithm learn from all those features and give you an outcome. For instance, recognizing a number. Now it's completely different. Thanks to deep learning, we don't have to spend time in handcrafting features, right? It's the model itself that learns this abstract representation for the data and we get an outcome. I would add though that we do have to spend this time in understanding better how the model is working, right? So I would argue it's a different allocation of our time, but we have to be equally careful. Yeah, that's super interesting. Then I think here they have an interesting paragraph about PyTorch for deep learning, which I'm going to skip because I think it's way more interesting. Why PyTorch? And they say PyTorch is easy to recommend because of its simplicity. And I think that's a key point. Many researchers and practitioners find it easy to learn, use, extend, and debug. It's Pythonic. And while like any complicated domain, it has its caveats and best practices, using the library generally feels familiar to developers who have been using Python previously. And I think so far that's how I feel. It's a code that looks very similar to me to what I have seen, for instance, with NumPy, right? And it says, but PyTorch offers two things that make it particularly relevant for deep learning. It provides accelerated computing using GPUs, and it provides facilities that support numerical optimization on generic mathematical expressions, which deep learning uses for training. And then, very important point, they say, note that both features are also using for scientific computing in general. So it's not exclusive for deep learning. In fact, we can characterize PyTorch as a high performance library which supports scientific computing in Python. So it's not limited to deep learning. It makes deep learning very easy and it's kind of a focus of it, but it's not the only thing you can do with it. And it's very, very expressive because of its eager mode. And, they will talk about eager mode later on, but I think it's also very nice to know that PyTorch has a compelling story for the transition from research and development into production. And that's something I mentioned already before. And it says, it initially focused on research workflows, but it has been equipped with a high performance C++ runtime that you can deploy, that it can be used to deploy models for inference without relying on Python, because Python is an interpreted language. It's not compiled like C++, so it's slow, right? So they are here closing this bridge. And they say it has also grown bindings to other language and interfaces for deploying on mobile devices. So it's edge computing also, right? Uh, yeah. So I think that was a pretty intense but very interesting paragraph. And the one that comes next, I also like it even more because that's where you clearly feel that the authors of the book have been in this evolution very like for a long time. And it says, though, while all analogies are flawed, it seems that the release of Pytorch 0.1 in January 2017, so like 3 years ago, more than 3 years ago, marked the transition from a Cambrian explosion like proliferation of deep learning frameworks and libraries and wrappers to an era of consolidation and unification. So we went from many stuff to, basically two options, which are TensorFlow and PyTorch, and they tell you like what happened. So they tell you at the time of PyTorch first beta release, you had Theano and TensorFlow that were like very low level libraries, and you had to, as a user, define the whole computational graph. We will learn what that means and then execute it. So that left like a caveat. And that caveat was covered by Lasagna and Keras, which were like high level wrappers around Theano, and Keras was also like wrapping TensorFlow and CNTK. That's that's the deep learning framework from Microsoft. And then you have like Caffe, Chainer, Linet, Torch, which is the Lua-based precursor of PyTorch. So we'll see more about that. MXNet, deep learning framework from Amazon, and others that they filled somehow little niches that were left in that ecosystem, right? Then PyTorch beta release 2017 January came out, and things in these 2 years like changed dramatically. And what does it mean? Basically, like um, Theano is dead. TensorFlow consumed Keras as its main API, and it had a very important release, version 2.0, that it basically used the eager mode by default. Then there is JAX, um, with basically is the whole idea of Google that has developed independently from, sorry, TensorFlow is supported by Google, right? That's a very important detail that I left out. While PyTorch, Sumit Chintala was doing his internship at Facebook at that time, so it's the deep learning framework of Facebook and OpenAI and others, many, many others. Yeah, so what else? Sorry. PyTorch, it consumed Caffe2 for his backend, replaced most of the low-level code reused from the Lua-based project, so that one we saw here, added support for Onyx, which is, a vendor-neutral way of describing models so that you can exchange them better, and then add, so to say, the graph mode. So you see, and they say it here, TensorFlow has a robust pipeline to production, an extensive industry-wide community, and a massive mindshare. Um, I guess you will see big giant Google promoting it a lot, and and Pytorch has made huge inroads with the research and teaching communities thanks to its ease of use, and it has picked up momentum as students like me left university and went to industry. But it's what they say is it's very interesting how the advent of TorchScript and Eager Mode, both for PyTorch and TensorFlow respectively, has set their uh, feature sets to converge. So we have TensorFlow putting Eager Mode and PyTorch putting TorchScript, so they are kind of converged. And finally, it says PyTorch release version 1.0 replaced CNTK and Chainer as framework of choice by their respective corporate sponsors. So now Microsoft is also using PyTorch. That's the big takeaway. And then this is also a very interesting chapter. It says an overview of how PyTorch supports deep learning projects, right? And the first thing you should know is that um, and that's a high level map of the PyTorch ecosystem. And it tells you PyTorch has the Py as in Python, but there is a lot of non-Python code in it. And it tells you, well, the reason is performance, because Python is an interpreted language, it's slow. So most of PyTorch is written in C++ and CUDA, which is a C++ language from NVIDIA that can be compiled to run with massive parallelism on GPUs. So that SageMaker notebook we set up in a previous video uses GPUs, and those GPUs run CUDA on them, right? So that's why it's very important. And it says, as we already touched on it, as its core, PyTorch is a library that provides multi-dimensional arrays, or also called tensors, and an extensive library of operations in them provided by the Torch module. So we did like import Torch, that's that Torch module. Both tensors and operations on them can be used on the CPU and on the GPU, and that's what we did, right? We moved from the CPU to the GPU. And that was super easy. We just like needed to change the device. So it was just one line code. And it says that the second core thing that PyTorch provides is the ability of tensors to keep track of operations performed on them and to analytically compute derivatives, which is super important for like deep learning and the output of a computation with respect to any of its input. This is used for numerical optimization. It's provided natively by tensors by virtue of by the AutoGrad engine. So AutoGrad is another very important part. Um, okay, long paragraph in here. Probably gonna skip this part, but basically it says by maybe one line, by having tensors and the AutoGrad enabled by having tensors and the AutoGrad enabled tensor standard library, PyTorch can be used for physics, rendering, optimization, simulations, modeling, and more. So it goes way beyond deep learning, right? That's another key message. And then it says the core PyTorch modules for building neural networks are located in torch.nn as in neural networks, which provides common neural networks layers and architectural components. Fully connected layers, convolutional layers, activation functions, loss functions can all be found in there. These components can be built and initialize the untrained models as we see in the figure. And then in order to train our model, we need a few additional things: a source of data, an optimizer to adapt the model to the training data, and a way to get the model and the data to the hardware that we will actually be performing the calculations needed to train the model. And then what we see in this figure is quite a bit of data processing that is needed before before the training data reaches our model. So first we need to physically get the data uh, from the storage data source, which could be like an EBS volume in our case, right, to some sample tensors. And then we will be aggregating these tensors into the batch and running a training loop in one or multiple GPUs, and we will end up with a trained model that we can deploy either in our own production server or in the cloud, as we are doing with AWS, right? So which are those key components? So it says we need to convert each sample from our data into something that PyTorch can actually handle, tensors. And this bridge is standardized by the dataset class that Pytorch provides in tensor-utils.data, right? So we are talking about data. We have a class called dataset in torch-utils.data. And this process kind of simplifies our life massively. And then, a few more things that says is, as I mentioned, the concept of batches that encompass several samples. And then it says this is rather elaborate, but it's also relatively generic. And Pytorch readily provides all that magic in a data loader class, right? And if you know a bit of fast AI, you have heard about these data loaders a lot. Yes, so what else? Then we also talk about the optimizer, which Pytorch offers as in torch.optim. And finally, we also talk about the option in training in one or multiple GPUs. So that's the torch.nn.parallel distributed data parallel or torch.distributed submodule, which offers that capability, right? So I think that's a very nice high level overview of it. And finally, to conclude, we have these hardware and software requirements, which we don't need to mention again because we have already done the setup in a previous video, right? So what I'm going to do now is basically, I'm just going to go over the summary, and we said deep learning models automatically learn to associate inputs and desired outputs from examples. Libraries like Pytorch allow you to build and train neural network models efficiently. Pytorch minimizes cognitive overhead while focusing on flexibility and speed. It also defaults to immediate execution for operations. Torch scripts allows to pre-compile models, so the opposite of eager mode, and invoke them not only from Python but also from C++ programs and on mobile devices. Since the release of Pytorch in the early 2017, the deep learning tooling ecosystem has consolidated significantly around Pytorch and TensorFlow, and Pytorch provides a number of utility libraries to facilitate deep learning projects. So yes, I think that concludes this book chapter. I definitely recommend you to check those. Make sure you're using PyTorch 3.6 version. Make sure that you can import Torch. Make sure that you have GPUs and so that CUDA is available returns true. And that's basically it. Have fun learning.